All right, welcome to the first video from chapter 2 of the book by Shankar. So the example problem shown is something we'd like to get to, and it'll become relevant, especially when we start doing dynamics problems. But I think even before we get to this example, we have to sort of motivate what we've done so far, and we'll talk about review what we've done so far and motivate why we want to talk about vectors, why we're going to have to generalize a little bit. Okay, so I just want to point out that so far in 1D, the direction of motion has been relatively straightforward, right? In 1D, in other words, you just have a line. And we do have in mind like what the positive direction is always. So like if this is the positive x direction, then delta x being positive means overall you've moved to the right. Delta x being negative overall means you've gone to the left. So in other words, we can, for 1D, we can specify direction just with a positive or a negative sign. Positive or negative, and that's it. We didn't really need to do anything else. Once you specify the direction, the positive x direction, you know what's the positive direction, what's the negative direction. But in 2D, it's a lot more complicated, right? You have, say you have an xy plane, you can go in any direction along here. So you have to be a lot more careful with, there's no such thing as just the positive direction or the negative direction anymore, even after you specify the coordinate system. So this is what's meant on the left here by review. It's sort of just like, kind of just looks like some random equations and then, okay, now we need to talk about something else. This is sort of why. So in 2D, whoa, that's not how you change the color. So let me point out some things that you already are sort of familiar with. And one is that you can describe displacements using vectors. So say we started at the origin right here, and we walk to the right some amount. We're going to wind up at this spot right here on the x-axis. And then say we walk up and right, some other amount. So our first travel, when we move to the right, we can represent that motion, that displacement, with a vector A. And we can represent our other motion with a vector B. Right? So a few things that I want to point out here. A and B here are displacements, displacement vectors. Okay. You've probably heard this before, but it's worth pointing out. Vector, for now, the way we can think about a vector is something. So in other words, that something could have units. Here it would have units of meters because it's representing a distance. So something maybe with units, and most often with units. Maybe with units. With both magnitude and direction. So in other words, my displacement vector A has some magnitude. Maybe I walked 1 mile, and the direction is in the plus x direction. B, you'd have to be a little bit more careful about specifying the direction, right? You'd have to maybe specify the angle that vector makes with respect to the positive x direction. Or you could specify like the x and the y components of this vector, right? So which will involve those separate pieces. So this is sort of what we need to talk about today, just specifying those pieces and what we mean by, and some definitions of terms like basis vectors and that sort of thing. Okay, so another thing that I want to point out is that, so we're often going to use delta R. So later, we'll use just delta R for this. So in other words, so R final minus R initial. Notice how any point that you're at right here, So I can just specify any point on the xy, in the xy plane, and that has some xy, x comma y coordinates. And I can imagine there's a vector, there's something pointing from the origin of that coordinate system to my point. So that's called the position vector. So R for point P. Point P, and this is P right here. Yeah, it has some x and y coordinates. So every point in the xy plane has a position vector. And these displacements, like what I drew A and B, those are delta R's. Okay. Another thing I want to point out, I'll just keep doing different colors until I run out. We can add vectors. So we can add these displacements. You know, if I walk to the right and then walk up and right, you know, in the direction and with the magnitude represented by displacement vector B, then where am I overall? Well, I'm, you know, relative to my starting point, this is where I'm at. So we want to be able to talk about the addition of these vectors. Right? So one thing I'll point out with that is we add vectors graphically using the tail to tip method. Okay, so notice how it's just like a chain of putting them together. So if you can write down A, and then where A ends, that's where B begins, and then you draw B on there. And then from the very beginning to the very end, that's where you draw, that'll be the sum of all those vectors. Okay, so your book also talks about this. It has A and it has B, and it chains them together, and then C is A plus B. So from the very beginning of A to the very end of B, that'll be the vector addition of A and B. All right. Now keep in mind that in general, so one warning, probably the most common mistake students make with this is that the magnitude of A plus B, so the length of A plus B, the length of A plus B is generally not the same as the length of A plus B plus the length of B. So notice how I'm writing down a lot of words here. Length of A, length of B, the length of A plus B. And that's because A and B are displacements, are lengths, SI units of meters. We have a more general way of talking about vectors and the magnitudes of these vectors. So the length of A, we can just talk about this right here. So absolute value of a vector. This means the length of that vector, and that can still have units. So this statement that the lengths aren't the same, that this length is not equal to this plus this. So all those words simplifies to this, there is an equivalent statement to this mathematical expression. Okay, so a vector with the absolute value sign means the total magnitude of that vector. So if the vector is representing lengths, it's going to be the total length with units. So when you take the magnitude of a vector, you're saying, I just want to know the magnitude of it, not the direction. So I don't care about the direction anymore. I care about the length, the magnitude. But later on, we're gonna add speeds like this. We're gonna add velocity vectors. So this is just another warning that when you add two velocity vectors, the total speed after you add the two is not necessarily the same as the speed of the first vector plus the speed of the second vector. So these vectors follow some algebraic rules that you're used to. And it makes sense that like if you add A plus A, you get 2 times A. So you can take any scalar, any real number times A, and that gives you another vector that will scale it up or scale it down, and it could even reverse the direction if that scalar is negative. So like negative A is a vector pointing the opposite direction. So this makes sense in terms of like if I walk to the right and then I walk to the left an equal amount, I overall have 0 displacement. So A plus negative A is 0. Yeah, that's what a lot of these words is saying right there. Okay, so the point of section 2.3 is that we want to make this a little bit more quantitative, right? So suppose A were what did I say before, 1 mile? And suppose B was 1.5 miles. And that angle right there is 45 degrees. We want to be able to talk about vectors more quantitatively so that I could know, for example, how far have I traveled from the origin to the end of point B? You know, how far have I traveled from, not what distance have I traveled, but what's my overall distance from where I started? Notice how that's the magnitude of vector A plus B. So there are a couple ways to do this. The most straightforward way for us, and the first thing we're going to talk about here is Cartesian basis vectors. Okay, so in other words, like if I'm looking at A and B, I can take any of these vectors and split it up into like its x piece and its y piece. And that's exactly what's going on to the left right here. So in the book shows this general vector A, which could represent a displacement, could represent something else like a velocity, you know, something moving in that direction with some speed. And the length of the arrow is how fast it's moving. But we're going to stick with displacements for now. So we can talk about the vector, which we put an arrow sign above it to talk about the whole vector, or we could talk about the pieces along certain special directions. So see how we've split this vector into AX and AY. Those are called components. Okay, so section 2.3 makes this a little bit more quantitative. So section 2.3 in Shankar is describing vectors quantitatively. And basis vectors will help us do that. Okay, so I hat and so by the way, I notice how I wrote down x hat right here. Sometimes I'll be using these interchangeably. So I hat, x hat, j hat, and y hat. Either of those two are specifying the two directions. So we're specifying a two-dimensional coordinate system. So we're saying that our vector is going to live somewhere in the xy plane, or the vector will be spanned by I and j. So if I draw a vector on top of here, I guess I've already used A and B, so I'm going to call this something else. I'll call this C. So C is my whole vector. I can think of this as two separate vector components. Well, I want to be a little bit careful here, but I can think of my vector as a sum of a vector along this horizontal direction. So I specified that this direction to the right is going to be what we call the I hat direction, and then the one up is going to be the j hat direction. So we have right and up. So we can call this maybe Cx and Cy. So our vector C is how much of that vector is along the x direction and how much of that vector is along the y direction. Now these are called vector components of our vector C. However, we more often use the word component to refer to something else. And that is not the vector component, but the scalar right here. So I'm going to write Cx is there's some number here times my x hat direction, or I hat. And Cy is Cy times y hat. So this is separating out, so like this red vector component, Cx, it has some magnitude and direction, right? This is kind of a way of separating out the direction from the magnitude. Now Cx could be the magnitude, but it could also be negative. So Cx is the x component of our vector C. It could be positive or negative. So like if my overall vector C, if it's overall, so it could be going up and right, could be going up and left, could be going down and right, it could point in any direction. If it overall has a rightward component, then Cx is positive. If it overall has a leftward component, then Cx is negative. If C is just pointing up or down, or if it's 0, then the Cx component is 0. And then the amount by which it's pointing right or left will be the magnitude of Cx. Okay. So it could be a positive or negative. It could also have units. If C has any units, it's living in Cx. It could have units. So if this is a displacement vector, it might have units of meters in SI units. X hat is called a basis vector. X hat and y hat are called unit vectors. So their only purpose in life is to point in a certain direction. They have magnitude 1. So the magnitude of x and the magnitude of y is 1. Remember I said that sometimes, so instead of x hat and I hat, they'll be the same thing. I hat and j hat have absolute value 1. So in other words, if we're talking about this right here, we're talking about the horizontal piece of our overall vector C. So our vector C has a horizontal vector component Cx, which is Cx times x hat. So normally when we say the x component of C, we're just talking about Cx, which could be positive or negative. So it's understood that the component is multiplying a basis vector. Right? Now these components depend on your coordinate system, right? I could have another coordinate system up, in this direction and in this direction. So instead of x and y, call this maybe u and v. So in that case, our vector C, our overall vector C, would only have a positive u component, and it would have no v component. It would have 0 v component. So the components depend on your coordinate system. And the coordinate system is kind of up to you. You're used to always doing like x hat is to the right and y hat is up. But in some problems, you don't want to restrict yourself to having to choose that. So let's see what the book does. The book it decomposes our vector A into the x component times I hat times I. Notice how they don't have the hat right there. The hat is just a shorthand to make sure that you know that it's a unit vector. But in your book, they'll just put the I bold and the J bold to refer to the basis vectors. When we write it by hand, most often we put the hat. Okay, so we need two pieces of information to specify a vector. So this vector C, if we knew its two components, Cx and Cy, if we knew those two numbers, we would know exactly how this thing points, how vector C points. But there's another way that you could specify the vector, and that is with magnitude and direction. So let me write down this fact. We need two pieces of info to specify a vector in 2 dimensions. So you could have, so one way is the x and y components. So let's say the vector is A. So we could have AX and AY. So by the way, this is assuming we already know the coordinate system setup. So if you knew ax and you knew ay, but you don't know what direction x hat and y hat are pointing, then they're kind of useless, right? So this is assuming we already know the coordinate system. We already know the coordinate system. So we could know ax and ay, or we could know the magnitude of a. So sometimes we'll just write a to refer to the magnitude of a. This is the same thing. This is the overall length, maybe with units of that vector. And so if we knew the length of like c right here, that wouldn't be enough, right? There's a whole circle full of points that all have the same length of the vector from the origin. So we would need to specify, say, the angle, where it's understood that the angle is measured counterclockwise from the plus x axis. Right? So you could be given magnitude and direction and some angle. So in other words, this is magnitude and direction. So either way, if you know the magnitude and the direction, or if you know the x and y components, then you know what the vector, you know the direction that the vector is pointing and its magnitude. You know everything about the vector. So your book is talking a little bit about the relationship between these two. So ax and ay you can write in terms of the magnitude and the direction. So ax is a cosine theta, ay is a sine theta. I want to warn you though that for these, so for equations 2.6 and 2.7 on the left here, those equations are true for any angle only if the angle is measured counterclockwise from the plus x direction. And the y hat direction has to be theta equals 90 degrees. So it's specific to x hat and y hat being like kind of what you're used to. And then theta measured counterclockwise from the x-axis. In other problems, like in this example problem we're gonna do, notice how I've chosen a different coordinate system. So we would not be able to use equations 2.6 and 2.7. And I'll show how we're gonna deal with this problem a little later. So I just want to warn you about 2.6 and 2.7. 2.8, that one's always okay. So that's just the Pythagorean theorem. That's always okay. So as long as your x and y directions are perpendicular, you can use that, right? The two legs of a triangle, when you square those two and then add them together, that's the hypotenuse squared. So that's fine. That one's always fine. 2.9, you got to be a little careful because, like, if you look at this picture, so theta could be, there's nothing stopping theta from being like in the third quadrant. So let's say theta is 210 degrees. So if theta is 210 degrees, both ax and ay would be negative. And if you plug that into equation 2.9, if you do arctangent of, and then a negative divided by a negative is a positive, if you plug that in your calculator is going to spit out an angle between 0 and 90 degrees. So your calculator can definitely help you out, but your calculator doesn't know, it doesn't know, it's going to restrict the values of theta that you can have. So basically my piece of advice here is that if you're converting between angles and components, to make sure that angle's between 0 and 90 degrees. And then you figure out the signs separately. Like ax and ay, you can tell based on your picture whether they're positive or negative. So any angle that you label in your picture, make sure it's between 0 and 90 degrees. And that's why 2.6 and 2.7, even though you can use it for angles that are not 0 to 90, you don't want to get in the habit of doing that anyway. Right? Also, your angle doesn't have to be measured relative to the x direction. We could have labeled theta the one relative to the y direction, in which case the cosine and the sine would flip here. Ax would be a sine theta. Okay, so you want to get in the habit of drawing a picture, and then sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. And then that will do you no harm. Okay. So this is just saying what I said before about the position vector. So that all the way up here. So this right here. For any point, you could just say, well, it has coordinates x and y. So x is the x component of our position vector r vector, and y is the y component. So you could write it exactly this way. Our position vector is x I hat plus y j hat. So I said sometimes I'll use x hat and y hat, x hat and I hat interchangeably. Other times I'll be a little bit more careful with, like, x is the coordinate, and then I hat is the basis vector. So here the book is distinguishing the two, but we also do that in handwriting using the hat as the unit vector, the basis vector, and then something without a hat is a component, if not magnitude. One final point, if you're adding vector, the reason we like components so much is that we can just add them together. So like for this right here, if we want to know the x component of a plus b, you can just take the x component of a and then the x component of b and add them together. So they would both be positive, and they add together, and that's clearly the x component of a plus b. Then the y component of a is 0, the y component of b is positive. You add them together, you get 0 from this one, plus something positive here. That's the y component of vector a plus b. So that's exactly what equation 2.12 is saying. You can just take the x pieces, the x components of two vectors, add them together, and take the y pieces and add them together to get the components of the overall vector, a plus b. So that's great if you want something a little bit more quantitative. So that will help you figure out exactly how big in magnitude that is. If you knew the magnitudes of the legs, you could figure out from the Pythagorean theorem the magnitude of a plus b. Okay, so the only thing left to do is to answer this problem. So there is a little bit of geometry involved in some of these problems. So here I drew a vector f, which is pointing vertically downwards, and it has magnitude 5 newtons. So we never talked about what a newton is. It doesn't really matter. It turns out it's going to be a force. It's a unit of force. But you could talk about 5 gigawatts, from Back to the Future. It doesn't really matter what it is. They're just coming along for the ride, right? Like in everything we talked about here with meters, nothing we really said depended on the fact that it was meters, right? So we have a force that's vertically downwards of magnitude 5 newtons, and we want to talk about the pieces in this coordinate system. So x is parallel to the ramp down the ramp, and y is perpendicular to the ramp. Right? And you can probably guess whether the x and y components are positive or negative. It looks like, so you might want to pause the video and guess yourself, but guess whether the x and y components of f are positive or negative. So we have f, which is pointing down. It has magnitude 5 newtons. And now the ramp, so remember the ramp was 90 degrees and this angle was 30 degrees. I'll do the complement with a double arc like that. So this vector we can break up into, so I'm imagining like this was our ramp relative to, so this was 30 degrees, remember? So we want to draw, so this vector has a piece along that direction and a piece perpendicular to that direction. So see, I drew the two vector components of our vector f. So our original vector was f. This is the x piece and the y piece. Notice how I didn't say x component. The x component of f is just a number without and not a vector. Right? So if we superimpose, so remember that there was a coordinate system that we had on top of here, and the x was actually pointing this way and the y was pointing this way. So if we look at our vector components of f, it looks like fx is positive and fy is negative. Right? So from this picture, we see fx is greater than 0 and fy is less than 0. So that's probably always a good thing to note right away. Are my components, for each component, figure out whether they're positive or negative. Okay. Okay. Let's see. So if this right here is 30 degrees, and this is where the geometry is involved a little bit. So let me try and convince you this way. So this is 90 degrees. If this is 30 degrees, this one right here has to be the complement, right? Because all three of those together are supplementary angles. So if my angle here is 30 degrees, that's going to be this one. So it looks like sine theta is opposite over hypotenuse. Remember, this is a right angle because our x and y pieces are definitely perpendicular to each other. So sine theta is between 0 and 90 degrees. So I'm just talking about the magnitudes now. We already figured out what we're going to do with the sines later. So sine theta is fx. And right now I don't care about, don't be scared of these absolute value signs. What they mean is I don't care about whether fx is actually positive or negative. I just care about the length of this thing right now. So opposite over hypotenuse. So this will help us solve for fx, the magnitude of fx. So fx is F, which is 5 newtons. Remember the units are coming along for the ride here. 5 newtons times sine of 30 degrees, which is 1/2. So this will be 5/2 newtons. And combining it with this fact, so Fx without the absolute value signs is going to be 5/2 newtons, right? Because we already know it's positive. So the magnitude is 5/2 newtons, and we know it's positive, therefore the x component is 5/2 newtons. Okay. Now, for the y component, it's pretty similar, except instead of sine, we're going to use cosine. So cosine theta is going to be adjacent over hypotenuse. And remember, we don't, with angles between 0 and 90 degrees, cosine of theta is definitely positive. So we just care about the magnitudes right here. So likewise, we can say Fy is F times cosine of 30 degrees. So this will be 5 newtons times square root of 3 over 2. Maybe I'll write this out. 5 newtons times square root of 3 over 2. Looks like this is 5 root 3 over 2 newtons. Not worrying about significant figures right now. And then because of this fact, Fy is negative, I have to go ahead and put in the minus sign. So Fy is minus 5 square root of 3 over 2 newtons. So overall then, in terms of our coordinate system, we can write F vector is, you can always write, it's the x component times x hat plus the y component times y hat. So F is, looks like it's 5/2 newtons in the x hat direction plus, and you could put the minus sign either here or with the minus, well, you just want to multiply by a minus sign once for Fy. So Fy, let's go ahead and stick the minus sign in with the number right here. So the n means newtons, by the way. So this is Fx is positive and Fy is negative. And we also figured out the magnitudes of those two things. All right, so this is the general strategy. You have a vector, consider it the hypotenuse of a right triangle where the two legs are parallel to the two basis vectors. And then, so figure out the signs separately from the magnitudes. So the magnitudes will involve sines and cosines. Yeah, and the signs should be obvious from whether the vector components, go with your basis vector or against it. Okay.